transition from what just happened, which was awesome. But we're going to do real analysis, damn it. Just settle in for a minute. Become aware of your body. Switch over from focusing on your thoughts to focusing on sensation, just for a few moments. And notice your breath. See if you can be in tune with an entire cycle of your breath. When it begins to the wraparound. Find yourself running out of air or any strain, you're probably trying to control your breath. You just want to let things happen and watch. Let's just gently come back to some real analysis.
You're good, I already started.
Oh, did you?
Yeah.
Oh, you're so kind. Thank you, Kayla. Let's see, it looks a little crooked. You didn't do that, I did that. No, there's no problem. I know, I was like, she's gonna think she did something wrong. She didn't do anything. All right. Well, good stuff. Anybody have any questions? Yay!
Okay.
Yes. Okay, I like the way that starts.
For 237,
Okay.
I've had a series of arguments with myself.
Good.
So
Good.
for A,
Uh-huh.
I made two sequences.
Mm-hmm.
And at first I convinced myself, they're both divergent, so therefore they must remain divergent. But if you make two piecewise functions, so like you make x sub n equal to 1 if odd and then 0 if even, and then y sub n equal to 0 if odd and then y if even.
Ooh, I like it.
So then you add them and then it's always 1.
Yeah.
Oh, okay. So I won that argument. That's good.
Yeah, you win.
So then let's see what other arguments I had with myself. So I don't know how I feel about a convergent and a divergent and then x sub n plus y sub n equals something that's convergent.
Yeah.
I don't know that I can necessarily put that together in my brain, like
Right.
visualizing that.
Let's see here. So you're talking about B?
Yeah.
Okay. So we know. So is there a way, so let's write up here on the board. And I want to try to get this to you without.
Giving me the answer.
Yeah, exactly. Yeah, pretty much. Yeah. Yes. As always. So we've got the sequence x sub n converges. We've got a y sub n diverges, but the sum converges, which sounds sus, right?
Yeah,
That's
it really
like,
does.
yeah. I hate it when I start using new slang. I'm not trying to like be cool or anything. I'm never actually trying to be cool.
I like it.
It just happens. So, what do you think, Kayla? Do you think this is possible? Just like your
I
instinct.
mean, no.
Yeah. Any other suspicions about this? Anybody thought about this and have some?
Well, so I also think it's impossible, but I couldn't figure out a theorem to point to say that
Yeah,
it's
that-
definitely
Yeah, that's it. Okay.
That's
It's like,
where I
it's
was.
like a long proof.
So, let me ask you, so here's the hint. Here's a convergent sequence, here's a convergent sequence. I know that I can take any two convergent sequences and add them together and get something convergent. I know I can multiply by a scalar, that is still convergent. Is there anything I can do with these to get this? And you just need to do a little bit of playing. Because if you can, then theorem, I don't know, algebraic limit
Yeah,
theorem,
yeah,
part
theorem,
7,
yeah.
what, yeah.
I've done that right now.
Does that make sense?
Yeah.
Yeah.
Well, there's a lot of sense.
Okay, awesome.
Oh, well.
That's good, no, that's good.
Too
That's-
bad I already finished it.
Oh, I'll be interested to see what you did.
I made a definition for diversion and proved it was divergent. You know, we don't have to discuss.
Okay, all right, fair enough. I guess I'll get to enjoy that anyway at some point. So, anything else here, Kayla?
Let me double check.
Yeah, or anyone else? Anything else to talk about here?
So in the limits for exercise 2.34, we're allowed to rearrange those and they're still the same.
Yes.
Okay.
Yeah,
I did that.
absolutely.
Because I did that.
And I just assumed it was correct, and I was like, I don't.
Yeah, I mean, there's not a whole lot to do
Yeah.
in that problem, right? I mean, basically, plug in the limit, see if everything still makes sense. And does that make sense what I'm even saying? Yeah, plug in the limit, see if it still makes sense. So like B is gonna bomb, so there some algebra is required.
Yeah.
Well, and then you don't want to divide by 0 in C, so yeah, some rearranging there, just a little bit of algebra.
Cool.
Not much algebra in C, sure, don't get too crazy. Kayla, have you thought of any?
I think I'm good.
You good?
Yeah.
Okay.
I mean,
I got office hours
Hesitant.
tomorrow, and
yeah.
If you need
and
to
I can-
chat, it's
I
all
can
good.
Visit you.
alright. Trinity, Diana, go through okay? Yeah? Okay. Okay. Wanted to show you something. So now I finally remembered how to do this and practiced. Let's see if I can remember again. Trinity, I actually promised to do this in 480, but never did. What do you think of that infinite sum? Does that add up to something?
It looks like it adds up to 0.
It looks like it adds up to 0, so you're like, Noah's looking at this and going, okay, so that's 0 plus 0, I think.
So
Yeah.
cut on up to 1 now, if you group differently.
Yeah, so this way if I group, I get 0. But if I actually just group, just hold off the first term, 1 plus 0 plus 0 plus 0, I could get 1 out of that pretty easily. So this series here is classically divergent. It never really settles down at all. And we're going to talk today about series and how do you even discern if a series has meaning? But before we do that, I want to show you something that was done by one of the great mathematicians of all time, Ramanujan. I say it like that. I've heard that Ramanujan. Ramanujan just flows nicely. I'd have to hear Ramanujan himself say it to know. But Ramanujan basically was a self-taught Indian mathematician who was just working on infinite series on his own. He was learning, he was working, and he just started doing some really interesting things. And he wrote them all up and he sent them to a mathematician who was famous at the time, Hardy. And Hardy looked at this stuff and was like, this is wild, but there's something here. Hardy saw something in his work. And one of the things he saw in his work was stuff like this. So let's call this A. Yeah, so this is A. And then what would 1 minus A be? So the game here is forget that this is divergent, like you learned in Calc 2. Just roll with it. Just do math with it. So that's going to be, and then we simplify. So you can see here that that's going to be 0 plus 1 minus 1 plus 1. Yeah. Just so happens that 1 minus A, whatever that quantity might be, is actually A again. So we have 1 minus A equals A. So I can solve this. So 1 equals 2A, and that means that sum must be a half. Even though there's not a freaking fraction in the whole thing. So this was Ramanujan's first observation, and then, just being a genius, inspired genius, went on to explore some other things. The next one he looked at was this series, and we'll call this B. And it was 1 minus 2 plus 3 minus 4 plus 5 minus 6, on and on, alternating sum with the naturals. Again, in our minds, that doesn't make sense because of our Calc 2 training. I mean, the one thing you do know, and let's just talk about this real quick, from Calc 2, we know that if a series converges, so writing less than infinity, that just means converges. If this then, the terms have to die out. When you're adding up an infinite pile of things, you want the things you're adding on to get smaller and smaller. If they don't, you're making a tower, right? So just imagine, Greg, you're building a stack of things. You want the things you're stacking to get shrinking at a pretty good clip. So the contrapositive of this is that if the terms don't die out, then the series diverges. And this is called the nth term test. We're going to be reviewing some series stuff. But it's a really great place to look if we're approaching things in a classic way, assuming that Calc 2, and you should do that. You should always assume your Calc 2 knowledge is legit until you go on to grad school or you go become a hermit and do your own thing. Or you're doing what Noah did. You create new you come up with your own definition of divergence, and maybe these don't diverge according to it. But you can see here the terms don't die out, so these do not converge in the classic sense by the nth term test. But let's take this series, and then we already know something about A, so let's look at A minus B. So we're going to take this 1 minus 1 plus 1 minus 1 plus 1. And underneath it, I'm going to put minus, and let's put this series. And line up the terms. I like to end on a plus minus as opposed to a minus plus, if I can. It really doesn't matter. And so we're going to subtract these two. So 1 minus 1, 0, negative 1, plus 2, 1, negative 1, minus 3. Roll along with me. See if we agree. Well, shit. I guess I'm landed on a minus plus. See if you agree with that. Because this is the kind of thing you want to show people. This is like bar mathematics, right? This is how you win a beer. Or just after a few beers, you pull this out. Back when I used to drink beer, that was a thing I would do. Flirting with alcoholism. Just go do the math. Just carry the math away. Is everybody cool with this? So look, this is the series B. So A minus B is equal to B. So A is equal to 2B. So in other words, B is a half of A, which we already know to be a half. So that adds up to a quarter. Somehow it became less. Okay, last one. Let's consider a series. These are already awesome and amazing, but this is the one that's most famous. Let's just add up all the natural numbers. And let's look at B minus C. Can you compute that? What is B minus C going to be? Is it looking good? Is anything, I heard maybe, was that you, Kayla? Maybe making some kind of noise and delight, or, no?
Generally laughing.
Yeah, okay, good. There's a lot to laugh about. I hope I got this right. Yeah, I got this right. Is this? Yeah, okay, good. Everybody, just make sure you're getting basically a sum of all the negative multiples of 4. And once you do that, realize that what you actually have is that, which is C. So B minus C equals negative 4C. So B equals negative 3C. So C equals negative 1/3. B, which is a quarter. And you get negative 1/12. So this sum adds up to negative 1/12. And then you say, well, this sounds like some grade A bullshit. I mean, it looks like bullshit, right? It certainly doesn't make sense in any way that we understand. But it turns out to actually be useful. and to resonate with another truth we can find somewhere else in mathematics that gives us the same value, which is crazy. It's also apparently, now I'm just going to step on a limb here, it's used in string theory. Some of these facts, like I think this one, and then that, these appear in string theory. But let me tell you somewhere else, which none of the physicists at Regis give any credence to. We're all experimentalists here. And so if a mathematician came up with some physics that can't be tested, they're not going to buy it. Good for them. Good for them. So there's a thing called the Zeta function, the Riemann Zeta function. And it's got many forms. One of the forms is this. So God help me on my zetas. Let's just pretend that's a zeta. Use anything you want.
Yeah, they're just squiggles.
Is that zeta-ish?
I think so. If I
Thanks.
remember correctly. It's like a weird squiggle.
You got my back. Thank you. It's a weird squiggle. I do that much, yeah. Dangerously close to my Koshi. All right. So anyway, so one of the forms of the Riemann zeta function is this. So the Riemann zeta function actually gives us all sorts of famous values, but notice that zeta, I have to repeat it, good lord, of -1. Oh wait, sorry, this should be this, apologies, sincere apologies. The zeta of -1 is literally our series. We ended up with that C. There's another definition of the zeta function that involves integrals. So there's like actually multiple definitions of the zeta function. And now I feel like I can't quite remember it. I gotta look it up and make sure. So let's see, I want you to see the integral form of it so you don't think this is just bullshit feeding bullshit, which would be a reasonable thing to think. It's like, oh, this fraud is telling the other fraud they're right. So let's see, where's my integral definition of it? And this is really one of the hot functions in complex analysis and in mathematics. Oh God, here's another form. Thanks, Euler. Or it's equal to, oh my God, this is so beautiful. The product of all over primes. So this stands for like a product, infinite product of 1 over 1 minus p to the -z. That's crazy. So just real quick, what does that mean? That means, because you're probably not used to seeing infinite products like this, but you take the first prime, which is 2, so that's 1 over 1 minus 2 to the -z times 1 over 1 minus 3 to the -z, and then just do all the primes. 5 -z, on down the chain, so it's equal to that. That's one form. I want my integral form. That one. Okay, here we go. So here's their zeta. Oh God. It's kind of ass backwards from mine. Sorry, just kind of babbling here. Pi to the z halves over gamma function, which you probably don't know either. Hold on. Well, I should have had this prepared. This is pretty half-assed. How about this? Equals many other forms. That is so sad. each one will take us into a deeper discussion, and I already feel like we're in so deep, and I just wanted to chat about this. But what you can show is that using these other forms, you can literally verify, using any of the forms, that zeta of -1 is -1/12. So don't use this version, go to one of the others, and you can verify this. And then when you know that zeta of -1 is that series, things start to tie together. Pretty crazy stuff. Pretty fun. It's actually really fun. It just makes me want to sit down and just try to figure out other weird infinite sums that we could come up with. But I wanted to start off today with a extended ramble, and I succeeded, on infinite series and what can happen when things diverge. There's a whole branch of mathematics just related to studying divergent series. I wish I'd known about that back in the day. That's really cool. There's clearly something happening. It's just we don't know what it is. So let's come back to the Earth. Back to Earth. Talk about an infinite series. What we do know and how we deal with it in real life. As close to real life as this can come. This seems very concrete after all that. Adding forever? Sure. So infinite series are written as a sum of terms. So these things are called, this is a quick refresher, these are the terms of the series. We usually suppress the indices unless it's really important. So indices suppressed when irrelevant or clear. Hopefully both. Hopefully both irrelevant and clear. So we know what's going on. The way we make sense of this is we convert it to a sequence. So to make sense of a series, convert it to a sequence. And that's why we need to understand sequences. So the sequence is going to look like this. S sub k. S sub 1 is the first term of the series. S sub 2 is the sum of the first two terms, and so on. And in general, S sub n is sum of the first n terms, and it is called the nth partial sum. It is a portion of the sum. So we look at the sequence of partial sums, and we analyze that. If that sequence converges to a value, we call that value the sum of the series. So if S sub n converges to some S, then we say the series, the original series, converges to S, and we can write literally it's equal to that. Now I have a note here, C theorem 246. Oh yeah, that'll be our next one. So in doing this partial series approach, you can understand all sorts of series. Let's take a look at actually applying this, just real quick, which will also give us a review of some things. Example, let's say consider the series sum a times r to the n, n equals 0 to infinity. We'll hold off on what r is. R is a constant. Anybody recognize that series? Like some, you know, you learn how to all these names. You call that geometric, beautiful, yeah. So when you write this thing out, it's a times r to the 0 plus ar to the first squared cubed. And what you notice here is that these all differ by multiplication by r. And so that's another way to recognize a geometric series. So if we want to understand when this converges and what it converges to, we have to look at partial sums. So the nth partial sum of this would look like a plus ar squared plus all the way up to ar to the n minus 1. Notice that if I have 3 terms, the last exponent is 2. If I have 4 terms, last exponent is 4, 3. So this will be 1 less in power than the number of terms, because we start at r to the 0. Now take this and multiply it by r. And you might want to do a little shifting here, because you're going to notice something cool. When you multiply this by r, everybody gets bumped up a power. And we'd still have one of these, but now we have, when you multiply this last term by r, you get that. Yeah? Does this ring any bells? You've seen this before somewhere? Yeah. It's good to see it again many times. So let's subtract down. So we've got s sub n minus rs sub n equals pretty much a beautiful thing. Everything cancels except the first and last terms there, so it's going to be a minus ar to the n. Over here now, it looks like I can solve for s sub n, which is fantastic. So this is just 1 minus r times s to the n. And so s sub n, the partial sum, nth partial sum, can literally be computed with this formula. So that's pretty cool. That's actually the sum formula for a finite geometric series. You can use this to add one of these dudes if it just truncates somewhere, just ends. But we are interested in something else. We are interested in the limit. So that's the nth partial sum. Now we ask ourselves, does that limit exist? So consider limit s sub n. Again, I'm suppressing all sorts of things emotionally, but this is a mathematical suppression. So this is lim of a minus ar to the n over 1 minus r. And don't forget, we might want to remember that n is the moving piece here, though. N is the part that's kicking. Everything else is constant. So when we look at this, let's see, we can actually break this down a little bit. This is going to be a over 1 minus r minus a times 1 minus r to the n. I'm just breaking it down so we can kind of think about it a little bit better. So now r is a constant. This is already fixed. This isn't changing. So all our action is going to happen here. What does r to the n converge to? So let's think about it. So if r is, what if r is bigger than 1? Like it's 2. What does that happens here? It goes to infinity, right? If r is a number bigger than 1, then subsequent powers get bigger. If it's bigger, so let's make a little chart. So here's 1, here's -1. So in this is r. Out here, we get r to the n goes to infinity. What about when r equals 1? What happens when r equals 1? Well, just that. just 1 all the time. Yeah, so so here, this converges to 1. What about inside here, when r is a number less than 1 in magnitude? It's fractional. We've got 0.98 to the n. What's happening there? You can think of it as you're always taking 98% of the previous value. It's going to head to 0 eventually, right? Eventually, whatever your discount price is going to shrink all the way to 0 if you keep discounting. So when in here, r to the n converges to 0, it's constant 1, and then out here again, this is a number like -2. This is going to alternate sign and grow in magnitude. So out here, r sub n diverges as a sequence. Here, this also kind of, you could say that diverges out there. So it looks like what we're saying, and then look, when r is -1, it diverges for sure, right? Because it's just alternating, 1, 1, minus 1, 1, minus 1. So it kind of looks like we're saying r must be in this interval, and I've included 1 for a minute. What does that series look like when r equals 1?
It's 0, right?
The sum, oh wait, so explain what you mean.
So if, oh wait, never mind, because the r is on the bottom. My bad.
Yeah, let's just look, yeah, I see what you're saying, yeah, because then you'd be dividing by 0 here, right? But if r is 1, this is what the series looks like. Yeah, so the partial sum is n times a, but what happens if you keep adding any number forever? Blows up,
Yeah.
as long as it's not 0. So for any number, if I keep adding it up, it's going to blow up. Think about the nth term test here. Terms aren't dying out, this series diverges. So we're actually going to strike off that. And now what we have is a condition for convergence, because that limit up there is going to exist. Here, I'll come back to here. Actually, let me summarize this here. So r sub n goes to 0 if the magnitude of r is less than 1, and it diverges otherwise. So we're going to make a condition, say that r has to be less than 1 in magnitude, and then in that case, this piece dies. And we have our sum. This series is equal to a over 1 minus r if the magnitude of r is less than 1. I gotta pee super bad, I'll be right back. It just came on like a wave. Oh yeah. I'll be right back. Hopefully that you've seen this before, somewhere back in the day. Now you own geometric series, and you can do anything you want with them. Let's take a look at another famous series class that you definitely need to know. So we got geometric, Notice that in geometric, the thing that's moving is the exponent. So here, the thing that is changing with each term is the exponent. Contrast that with this. Where now the base is the thing that's changing. And so this looks a lot like that. This is basically like that Riemann Zeta function in some ways. It's 1 over 1 to the p. It's 1 over 2 to the p. Oh, no. What do you call these?
P-series?
That's right, yeah. Yeah. P-series. These are a lot trickier. One of the famous series, the great series, falls into this class. And that's the Harmonic Series. And this thing is divergent. But notice its terms do die out, right? And that's one of the interesting things about series. There's some really counterintuitive things happening here. It looks like this. The terms are dying out, but it still diverges. It just keeps piling up very slowly, but it keeps piling forever and ever. There is no upper bound on those partial sums. So let's talk about how to show, let's find a condition for convergence using a theorem you've never seen before unless you've read ahead in the book, the Koshi condensation test. And we really should teach this in Calc 2. I don't know why we don't. So we will use,
That's pronounced Koshi?
yeah,
It's Koshi.
Koshi. How are you been pronouncing it?
I would say that's Koshi.
Yeah, I think Koshi would say it's Koshi.
What language is the group?
Oh God. I don't know.
I'll just accept it and move on.
Okay, it really doesn't matter. It's really, as long as you don't call it like cocky or cokey, anything like that. I think you're good. Everybody will know what you're talking about. No, you call it what you damn well please. So use the Koshi
He was French.
condensation test.
Yeah.
What was that?
He's from French.
Oh.
I don't like the French language.
Yeah, fair enough.
They have so many useless letters.
Noah's really pouring his heart out today.
Who was?
Noah is really pouring his
Yeah,
heart
he
out
is,
today.
yeah.
Sorry, I don't have a filter anymore.
It's all right, man. Just let it loose. You're safe here.
Yeah, it's good.
We're here for you. This is real analysis. You should feel free.
To really analyze the inequities in French language.
Absolutely. Absolutely. So, I don't know this off the top of my head. I mean, I know the idea. I just want to get the exact statement up. And we're not going to prove this. So, suppose B sub n, you should read through the proof. It's pretty neat. And we'll talk about the basic idea. Suppose B sub n is decreasing and non-negative. That's for all n. Then the series converges. So if I add up all those B sub n's, and when I write less than infinity, that signifies converges. If and only if, this will be a very strange condition that we need to talk about, the sum 2 to the n b sub 2 to the n equals 1 to infinity converges. So this series here, let's maybe write out what this looks like. I think we are starting, let me make sure we start the index at, we start at 0, sorry. Start at 0. And it looks like we start at 0 over here as well. So this series is going to look like this. When n equals 0, we've got 2 to the 0, b sub 0, wait, b sub 2 to the 0. Let me just go slow so I don't screw this up. 2 to the first, b sub 2 to the first, 2 squared, b sub 2 squared. Now we got the rhythm, so this is going to be b1 plus 2b2 plus 4b4 on up. The basic idea for this is as follows. Let's just talk about why this even makes sense. Because here you are skipping so much. And the further out you move, the more you're skipping. But if we take this original series, like this, and I should probably go. And look at what this sum is here. So first off, here's B1. So we're going to pull that. And then 2B2. And then 4B4. Yeah, I guess. Oh, okay. I'm also missing the B0. Okay, that was the rhythm was throwing me off there. And then the next one's going to be what, 8B8. So let's see. So we're multiplying this by 4, this by 2, this by 1, this by 8. So since the series is decreasing, we're assuming that B sub n is decreasing. That means as you move across here, everything is going down in value. So if instead of these, hold on a second here, I'm a little, yeah, I got the rhythms right. The grouping is what's concerning me. Let me write this little grouping up here so we can see it. So we've got B1. B1 plus B2 plus B3. And group those together. Plus B4 plus B5. Those together. Oh, okay. Now I see. Now I see what's up. Okay, so this series is decreasing. Notice that we can group them into these increasing powers of 2. And so if we were to use these guys here and say, replace this piece of the sum with 4 copies of B sub 7. Oh, wait, no, sorry. 4 copies of B sub 4. That's right. That's going to be greater than this sum because each of these values is less than B4. So that little piece right there is less than B sub 4. Now, this little piece here is less than 2B2 because B3 is less than B2. So if I replace it with a copy of B2, value goes up. And then out here, we go all the way out to B sub 15. This is going to be less than 8 times B sub 8. So what we're saying, this has to have this decreasing property, otherwise this doesn't work. But you can say to yourself, okay, look, if B1 plus 2B2 plus 4B4 plus 8B8 on down the way, if that converges, if this thing converges, then the original series has to converge because it's less than that. So original is less than this. And so if that converges, this converges. We can get the if and only if by playing a similar argument here. Let's see, I think they leave it to us as an exercise. Yeah, we'll not go the other direction. But so the whole idea here is this grouping together into powers of 2. We've at least got one direction. We've got this implies this. And frankly, that's going to get us a lot. It's definitely going to get us what we need over here. Maybe we'll check it out as an exercise. I'm not threatening that or anything. I think it might not be a terrible idea. So we're going to use this result, which is vaguely, hand-wavingly justified. So let's consider the p-series. So according to Koshi's condensation test, if I look at this version of that series and determine when it converges, I'll know this converges as well. The Koshi condensed version looks like as follows. So we have sum n equals 1 to infinity. And notice how you replace n. First off, you have a 2 to the n out in front. And then you only grab a sub 2 to the n. So here, a sub n is 1 over n to the p. Just trying to work this into shape. So this is sum 2 to the n, and then that's going to be 1 over 2 to the n to the p. And then I can simplify that. I guess we could actually just cancel this out. You could just cancel one of the powers of 2 to the n out, and you get this. See if you believe that. And check me too, please. Sanity check. Subtracting exponents, np minus n, pull the n out. Okay, so looks like now we have a geometric series. Right? This is actually just a geometric series, which we understand completely. So this is sum n equals 1 to infinity of, let's make it look more geometric, 1 over 2 to the p minus 1 to the nth power. So what's really cool about this Koshi condensation test is we turn something not even remotely geometric into something geometric, and then this makes the analysis a lot easier. That's the power of the Koshi condensation test. So this is geometric. And it converges when, this is R right here, when 1 over 2 to the p minus 1 is less than 1. And since this thing's positive, I don't have to worry about those absolute values. That means basically that 2 to the p minus 1 has to be greater than 1. When will that happen?
P is greater than 2.
Definitely that. Can we get a little tighter?
P is greater than 1.
Yeah, because when 2 to the 0 is 1, right? So
Yeah.
as soon as I move that exponent to be bigger than 0, we're bigger than 1. So we need p minus 1 to be positive here. In other words, p has to be bigger than 1. And that's the classic p-series condition. So we know that a p-series converges when, so this converges, we don't know what to, that's a whole other thing, when p is bigger than 1. Bless you. So let me ask you a question, my friend. So let you get caught up. And I guess I should ask, are there any questions for me first on this? So I wanted to give you a series to analyze, which is, of course, is none of the kinds we've discussed. So here's my question to you. What about sum 1 over n natural log of n? And I think n better start at 2, otherwise we're going to have a problem with division by 0. This is like one of the hard ones from Calc 2. This is one of those where you try to use a comparison test, a ratio test, and they all end up bombing. You've only got one test to use so far in here. I would recommend Kochi's condensation test. Now you got me wondering, no, I'm gonna look it up. I found out I've been mispronouncing, my sister corrected my pronunciation of a 70s TV show character the other day that I've been calling the wrong name for years.
Ooh.
On Good Times, they had this neighbor, and I've been calling her Malona. And I said that, and my sister said, "Who are you talking about?" And I was like, "The neighbor, Malona." And she's like, "It's Willona." And I was like, "No, you didn't. No, it isn't. No, it isn't." And she's like, "Yes, it is. Yes, it is. Yes, it is." And I was like, "Let's look this shit up." Apparently, my internet wasn't working right because I couldn't find my claim.
Koshi.
At least the anonymous voice on the internet agrees with me. You might not ever want to go back to any other test after this test. It's ridiculously powerful. Got me wondering what Koshi's nationality was. I know that Lagrange was not actually French, but that's not anything to do with this. He was French. Yeah, sorry, no. Is this looking? Yeah. What do we think it does?
This one not divergent.
Divergence, yeah. Because we've got, basically we end up with this harmonic series, or a multiple of the harmonic series and a multiple of infinity, still infinity, so we get divergence. Cool test, really cool, because these really are the really brutal stuff in Calc 2. Yeah. Sorry, I was trying to think of new problems to do, but I think I've tortured you enough with this stuff, so we'll call it a day. Yeah. Is there any questions on any of this, any of the machinations I've done? I'm going to ask you for Wednesday to please read. You definitely, I think, will want to have a sense of what we're talking about on Wednesday. It's going to get a little heavier. I don't consider this all super heavy, but this will be very new. Sorry.
This isn't heavy.
This isn't heavy, no, but so we're going to start talking about one of our big theorems, Bolzano-Weierstrass theorem, and subsequences of sequences. And so things are going to get really interesting. Really interesting. Yeah, so I don't want to.
And homework is due today, right?
Is that right?
You said Wednesday.
Did I say Wednesday? When do we want to do?
I don't know. It's
Wednesday?
done when you want it.
Okay, Wednesday's great. Wednesday's great.
Yeah, because you wanted us to have today to ask questions.
Yes, yeah. So that all sounds good to me. I'm pretty easily malleable if you all just gang up. Like all you have to do is just decide ahead of time. And then math club today. I think it's game night. It's the first meeting of the season.
Yeah, show up. I will if I'm awake.
You what? You will if what?
If I'm awake.
Oh, gee.
Hours.
Well, afternoon nap is a very healthy thing. So.
Yeah, I didn't get any sleep last night.
Oh no.
Not till I can try.
Did you stay up work?